देखो जरा, मैं स्टार्ट हो गया। पहले देखो आ रहा है या नहीं आ रहा। हेलो, यूट्यूब पे देखो। आया? आ गया? हाथ हो गया? आ गया, आ गया। दोबारा रिफ्रेश करो। आ गया। So hello everyone, this is Dr. O.P. Verma from NIT Jalandhar. Now we are going to start our second session of day 1 of CCTA 2020. So is my voice is audible? Can you, Dr. Ravi Verma, can you say? Can you check my sound? On the YouTube पे हाँ इस पे आ रहा है यार। हाँ तो रहा है। सब हेलो हेलो, पता नहीं क्या है। मोबाइल पे देखो ना। A very good morning, sir.
Good morning, Ravi.
This
So
is
this is
Dr.
Professor.
This is Dr. O.P. Verma, sir.
Okay, Professor.
No
Okay,
problem,
good
sir.
morning. Good afternoon.
How are you, sir?
I am fine, thanks. How are you doing?
Fine, sir. Just we are proceeding, sir. In 2 minutes. Okay, sir. In 2 minutes we will
Sure.
start. Okay, sir.
Sure, no problem.
Okay. चेक करो भाई, ये चेक क्यों नहीं कर रहे हो?
Yes, please, we can. Okay, sorry. Hello, Professor Ravi. Good afternoon, everyone. So, as first of all, I would like to thank the organizing committee for inviting me to offer and to present my work over here under this workshop. So, my presentation, I am just so is my presentation visible to everyone? Yes. So, shall I start? Okay. So, I don't know. Composites and nano composite, both these words looks very similar. And when I am talking about mechanics word, when we are dealing with mechanical engineering, I will say mechanics is very common thing. But going in details in mechanics is really still complex, and I feel still I reach only 10% of this word mechanics, despite being an associate professor. So, considering that BTech students, MTech students, and industrial persons from industries are taking or listening to me, so I designed my lecture in a way that all of them will get some information out of this lecture. Even if you get 5% things, and if you remember 5% of my lecture for at least 1 year, I will say that it is worthwhile. Do not try to memorize everything. Only 5% things if you remember when somebody is talking in front of you about composites, and if you remember 5% things, this workshop and my lecture is worthwhile. So I am moving to the next slide, which discusses about what are the contents that I am planning to discuss during my this short lecture. Introduction to composites. How we can classify composites? Composite can be classified in many ways. Characterization of composite. One of the main challenges that we are facing with composite, how to evaluate, characterize these composite properties. Macro mechanical analysis, micro analysis. We all discuss these words macro and micro in our day-to-day dealings when we are dealing with engineering. Like micromanagement is a very common word we are using in our day-to-day life. This manager is very micro, he goes at the very micro level. It means I am talking about finer details. Macro, I am talking about broader aspect. Then challenges with the nanofluids. Nanocomposites. When we talk about nanocomposites, the word starts with nanofillers, nano reinforcement. The only difference between composites and nanocomposite is the size of the reinforcement. In one case, it is conventional in microns, whereas in nano, because this time the presentation is only one way, the communication is only one way. So I am really sorry, because this is my first lecture on this kind of platform. Otherwise, normally I keep on interacting with the students. What is the meaning of nano? It means I am talking about at least one dimension that is in nano regime, in nanometers. And finally, I come to nano composite. We discuss how we can study nano composites. Most of the things that I covered in nano composites or nano fillers are from my own research. History of composites. We are using composites in our day-to-day life. Even if I am talking about brick made of clay reinforced with clay, again I am talking about composites. How composites are different than alloys? The first thing that comes into why I am dealing with composites, why I am talking about composite, why not I am talking about alloys. We all know what are alloys: iron alloys, ferrous alloys. Those who are in BTech or those who are in higher levels, iron carbon diagram is the first thing that we learn in the course of material science. If we memorize that diagram, whole course is over. So it means I am talking about alloys in which chemical reactions takes place. Iron and carbon, they mix each other, make chemical forms. Chemical reactions take place. The faces of iron and carbon are not separable. We call them alloy. There are different alloy: brass, bronze. These are duralium. These are some of the common alloys we are talking about in day-to-day life. And in all these cases, I brass. There are two metals, but they are not physically separable when I am talking about brass. Similarly, when I am talking about bronze metals, again we are talking about an alloy and the faces are not separable. But when I am talking about composites, again it is a mixture of two things. One, reinforcement. Second thing is the matrix. Matrix is the material that covers the reinforcement. In RCC, the iron steel rods we are using is reinforcement that helps in improving the bending stiffness. Wood, again a composite where one is reinforcement, cellulose is reinforcement, lignin is matrix. So this is a good example when I am talking about composites. So we are using composites in our day-to-day life. Again, composites means I am talking about mixing of two materials in such a manner that their physical phases are still separable. No chemical reaction takes place. There is still physical phases are still separable, and that's why I call them composites. So this is one of the some of the natural examples that I have when I am talking about composites. Next thing is advanced composite material. When the composite terms were introduced in early 90s, mainly composites, and still I will say most of the application of composite materials are in aerospace, space research, even in this cryogenic temperatures you are talking about, where we are going to deal with cryogenic temperatures, mainly in space, where temperature goes down to minus 200 degrees Celsius, or in the regions and the North Pole or something Atlantic, where the temperature goes down to minus 50, minus 60 degrees Celsius, or even lower than that. So it means we are still looking for composite materials. Earlier in 1990, when the composites were introduced, they were referred as advanced composite materials and were used in aerospace industry. Some of the examples that I have about composites is carbon fiber epoxy, where carbon fiber is reinforcement. Epoxy is a type of a polymer, is a thermosetting polymer. Epoxy adhesives, if I remember, we are using it from our childhood. Epoxy. So epoxy is going to be here the matrix. Glass fiber epoxy, another kind of a composite. Reinforcement is changed. Aluminium particles and aluminium, again another class of composite. Matrix is changed, reinforcement is changed. Now I am moving to my next slide. Here in this figure you can see three colors, three circles. The outer big blue circle, then a smaller and like this is the front face of a big pipe. This is the front face of a big pipe. I mean, I'm considering it like this. So there are three materials that I am going to talk. The red one is the most important, that basically governs the property of a composite. So what are these three phases? First thing, matrix. I am talking about the material that needs to be reinforced because matrix has weak properties. I want to reinforce it for higher strength. So I call it matrix. Then I reinforce it by using fiber that is red color. It can be a glass fiber, it can be a carbon fiber, or if the dimensions of these fibers are in nanometers, I can call it nanofiber. Then there is a third thing, white region. I showed three phases. What exactly is this? This is going to be the interface between matrix and fiber. So whenever we apply any load on this phase, I will apply load to the matrix. By using this interface, all the load will be transferred to fiber, which is having a superior mechanical or whatever properties we are talking about, mechanical, thermal, it is having. So it basically governs the overall properties of the composite. Overall, this is referred as a composite material or a composite pipe. So I referred it and divide the composite phase into three phases: matrix, fiber, and phases. So in this case, this is basically the composite material or the overall view of a composite material. So interface plays a very important role. Even when I am dealing with the nano composites, I am working in the field of nano composites, and I still feel interface plays a very significant role. If I even, because I know the properties of the interfiber. Fiber is having a very superior strength. Just to think yourself, you are having a steel rod or a rod, iron rod. Just put some plastic surrounding it. Now you will apply some load. Where all the load will go? You will realize you cannot stretch it because that steel rod is governing the mechanical properties of that overall object that is surrounded. That steel rod is surrounded by plastic, but it is not the plastic that is governing the deformation. It is that steel rod that is governing the deformation. Think yourself, even in your pen, pencil, whatever you have, if you start stretching it, it's not the pencil outer wood, it is the inside graphite that is governing, that is deforming, that is governing the overall mechanical properties. So in that case, fiber is the one that is governing the properties. Now, when we are talking about composite, composite can be of different types. I can classify composite based on matrix. As I told, there are three phases in composite: matrix, fiber, and the third phase is interface. I can classify composite based on all three of these. Simplified matrix. A composite can be a polymer matrix, where the matrix is going to be a polymer. Metal matrix, like aluminium, aluminum based alloys, copper based alloys. I call it metal matrix composite, where metals are used as a matrix and we have different types of reinforcement. Then the third is ceramics matrix. Ceramics matrix, like aluminium we are using. So it means we can classify composite based on these three categories: polymer, metal, ceramics. Further, polymer matrix can also be classified under thermoset polymers, thermoplastic polymers, and rubber. Thermoset and thermoplastic, I do not need to classify or explain anymore further, because we all know what is thermoset and what is thermoplastic. Thermoplastics can be regain its strength, and we can remodel it by raising the temperature about the glass transition temperature, melting it, and then again remold it. Whereas thermosets, it's not possible. It has a degradation temperature, and it finally starts degrading if we start increasing the temperature. Another way to classify the matrix, another way to classify the composites, and I will say reinforcement. I can classify composite based on two things: what is the type of reinforcement I am using, and other thing is what is the geometry of the reinforcement I am using for manufacturing or for generating or for synthesizing the composite. Continuous fiber, if you see this one, unidirectional lamina composite fiber, it means fibers are of long length. It goes from one end to the other end of the composite. If I am talking about a composite plates, it means the length of the fiber is from one edge to the another edge. I call it continuously fiber. Short fiber is the top one, right side, top image. It's short. Second image, also short. Third thing is particle reinforced. Particle reinforced means like carbon particles, spherical particles. Right side, third image, bottom one. It gives me another way. So this is another type of classification that we have when we are talking about composite. It means first we have geometry. Then I can also classify composite. Okay, it's a carbon fiber reinforced composite. It's a glass fiber reinforced composite. It's a Kevlar reinforced composite. So it means the type of fiber that we are using, we can classify composites based on that basis as well. So these are some of the ways how we can classify composites. So that these are the two main aspects to classify composites. Advantages of composite materials. I talked a lot about composites. What are the advantages of composites? Specific strength versus specific modulus. If you see, here I am not talking about specific, I am not talking about strength and modulus. I am talking about specific strength, specific modulus. This is a graph that is plotted between specific properties. What is specific? Why we are talking about specific in terms of composites? Whenever we are dealing with composites, we normally talk in terms of specific. It means mechanical strength divided by the density of the material. When I divide it by the density of the material, higher the density, lower is going to be the specific strength. Lower is the density, higher is going to be the specific strength. Metals normally have low specific strength because having a very high density. Polymer based composites are very light in weight, are really very light in weight. They are used in aerospace industries because their every inch, every gram of weight needs to be paid. I need a bigger engine to lift a higher weight. So I want to reduce the weight as much as possible. So here when I am talking, if you see this graph, fibers are on the top right hand corner, high strength carbon fiber. So in this case, I can clearly say when I'm dealing with carbon fiber is not a composite, only fiber. It is having a superior strength. Then on the left side of the carbon fiber, we have aramide fiber. Again, high strength, but the modulus comparatively to carbon fiber is low. Then if you come down, you can see CFRFP, just below UD laminate, CFRP. It means I am talking about carbon fiber reinforced polymers. So it is still high because now I am reinforcing it. When I am making a composite, the fiber normally takes about 60% of the volume. Rest of the volume belongs to matrix. Pure fiber is having a very superior strength, but when I'm talking about composite, there is also a matrix. So both of them, when it comes to carbon fiber reinforced polymers. Then we come to the bottom of this. At the bottom of this, I can clearly see, you can see high strength alloy, high strength steel, aluminum alloy. You can see them in the bottom of this curve, extreme left, very close to the origin. It means when I am talking about properties, specific properties, these materials have a strength that is very low as compared to fibers. Then also we have unidirectional woven. In unidirectional, the direction of the fiber is in one direction. It means I am just covering from, if I have a plate, I just have a fiber in X direction, along the X direction. I call it unidirectional. But if I have a fiber alignment that covers both the edges, means if the plate is lying in an XY plane, if I have a fiber along X direction as well as around Y direction, that makes a perfect cross. We call it woven fiber. So these type of composites also have different types of strength, and the strength of a composite depends on the orientation of the fiber as well. We will discuss it. What are going to be the advantages of the composites? When I'm talking about polymer, it means what is the biggest problem that we have with the metals? When we have metal pipes, what is the biggest problem that we have with these materials? Metals are very heavy. Metals are corrosive in nature. So if I am talking, and like these days, metal pipes have very high wear. It is corrosive in nature, plus heavy in weight. Whereas if I replace these pipes, normally in Canada, if you go in northern part of Canada, they are replacing these metallic pipes with composite pipes, and the reason is high corrosion resistance. So the maintenance cost is drastically reduced. I do not need to rotate these pipes because of wear, corrosion regularly. I can take the advantage. High impact resistance. High impact resistance, where this impact resistance comes? When I am talking about space structures, I need, because the debris that comes and that damages the parts. So high impact resistance despite having a low weight. We are using this composite in automobiles as well. In automobiles, weight is low. Now these days, whenever we are going to purchase a car, what is the main question that we asked at the dealer end? Still, if we are purchasing a Honda City car, what is the first question that we are asking? As an Indian, I can say I just asked two questions. My first question is, what is the average? Because we are more interested in average. One. Second thing is capacity of the engine. How much cc engine is this? Now if you see, Honda cars are very light in weight. The big cars are very light in weight and very high power, and the reason is because they are using composites in most of the as a material for manufacturing of most of the components. So high impact resistance. Then we have high wear resistance. Again, I talked about ceramic based reinforcements. High wear resistance. Resistance to extreme mechanical environment conditions. When we are talking about extreme temperatures, suppose I want to make some structure, space structure. What do you think at the daytime? What is going to be the temperature over there? If the temperature is somewhere around 150 degrees Celsius in the daytime, what is the temperature in the light in the night? Minus 150 degrees Celsius. Overall range 300 degrees Celsius. Every material has a thermal expansion coefficient. So what do you think? The dimensions, tolerances for that I manufacture or design the component, it works in such a range of temperature from minus 150 to plus 150? No, it cannot work. The dimensions will definitely change because my material will contract in the night and will definitely expand in the daytime. So it means I need a composite material that will take care of this, because there is no metal I know that will take care of these things. So again, composite comes as a survivor. Carbon reinforced carbon matrix, resisting a temperature of 13 degrees Celsius for a space shuttle. Space shuttle, we are using carbon matrix, carbon fiber, everything is made up of carbon, because it can resist a temperature of 3300 degrees Celsius. Carbon epoxy composite. Read this line very carefully. Carbon epoxy composite, near zero thermal expansion. It means the overall alpha of the composite is going to be zero. So it does not have any effect on the temperature because epoxy is having a positive thermal expansion coefficient, whereas the carbon is having a negative one. So when I mix these two materials and I make a composite, the overall thermal expansion coefficient is going to be negligible. So when I subject these structures to a range of temperature, my material will not expand and contract. This is one of the advantages that we have when I am talking about composites. Tolerable properties. This I will mention here that the one of the major advantages that we have with the composite is the word tolerable. What is the meaning of tolerable? Tolerable means I can play with the properties of the material. What about conventional properties? Conventional materials, I cannot do this thing? Yes, I cannot. If I have a conventional materials, most of you are working on abacus, ANSYS. What exactly you are doing? You are having a geometry, you are applying some load, and then you calculate the stresses of beautiful blue, green color stress distribution, and you identify, oh, this color is red. It looks, the different colors will give me an idea. My results are perfectly fine. Now I have a different colored images. But what exactly I can do if I identify that some regions having a very high stress, I will immediately optimize the geometry because I know I cannot change the property of the steel that I'm using as a material. Can you play and change the steel properties? No, you cannot. You cannot do this thing. So I can say that I can select a material and design for shape and size. This is conventional materials. When I'm talking about conventional materials, it means I am talking about metals and alloys. Composite materials. Here I can change and play with the material properties as well. So I have two design parameters over here. One is shape and size, as we already have. Other one is material. I can also play with the mechanical properties. If I switch, if I change, varying the property of the reinforcement, I can change the properties of the composites. This is one of the basic thumb rule in composite. I can manage, tailor the mechanical properties, thermal properties according to my need and desire. That's why we can use composite materials at a very high temperature as well as cryogenic temperatures as well, because I have this thing tailorable in my hand. I can tailor it. Even at cryogenic temperature, I know if I am talking about cryogenic temperatures, I know which fiber I have to use, which matrix I have to use, and exactly which properties I am looking at. So select appropriate combination of reinforcement and matrices, select optimal fiber orientation and layup sequence, and finally I can design it for both. I can design it for both. If you see over here, fibers are wrapped around. Fibers are wrapped around. In first case, when it's wrapped around, it will take bending, it will take hoop. But when I am subjecting it to torsion, the fiber orientation you can see over here on the pipe is changed. The matrix, the fiber orientation is changed so that it can account for torsion as well. This is the way I can manage. I can manage the tailorability of the material properties. So I can tailor it for both. What are the challenges when I am talking about composites? Quickly, I am talking about composites. I talked about many advantages: high impact, low weight, extreme environmental conditions, and then I say that one of the biggest challenges is I can tailor. Oh, sorry. The biggest advantage is that I can tailorable. The properties are tailorable. Now I am talking about challenges. What is the reason that we are still limiting the application of composite and nano composites are still limiting to is aerospace or very specific application? I don't know how many of you are playing lawn tennis. If you are playing lawn tennis, just go to a market and just purchase one racket of a lawn tennis. Earlier, if you remember, when we saw Wimbledon in 1980s and 1990s, the rackets were made up of wood, then some metal component, aluminium, reinforced. And now you go to the market and ask, what is the cost of this racket? He will show some wooden racket. So this wooden racket will cost you around 500 rupees, 100 rupees, 1000 rupees, 200 rupees. That this one is having a very superior metal, light alloy. You will get this racket for 10,000 rupees. Then, sir, he will come up with, sir, this is a carbon fiber reinforced composite racket. It will cost you something around 10 to 50,000 rupees. And you see it is having a superior strength, very lightweight, very light in weight. Whenever you go to a Nike shop, just look at the face of the customer care agent that is working on the store. First thing he will do, he will put the shoe in your hand and say, sir, see, what is the weight of this shoe? And you say, oh, it's very light. It looks like that it is just 100 gram. And the reason is we are using a very superior class of composite material for the manufacturing of the sole, manufacturing of these shoes. That's why they are very light in weight, but having a very high strength. Now, I am talking a lot about composites. Only positive things, or there are some negative things? Yes, there are certain negative things. The first thing, I give you an example of that lawn tennis racket. So in lawn tennis racket, what I say when I am talking about lawn tennis racket, light in weight, having a very superior strength. But my dear friend, the cost is 50,000 rupees. The cost is very high. I cannot purchase it. So cost is one of the big issues that we have when we are dealing with a composite material, specifically the fiber. What type of fiber we are using? Carbon fiber is very expensive. That's why we are using it for the manufacturing of the nose of the space shuttle. Very fiber, superior properties, but the cost is very high. Other thing is, if you see in a metal, the metals are normally isotropic in nature. I hope you understand the word isotropic, orthotropic, and transversely isotropic. Metal is isotropic in nature. I only need E, Young's modulus, Poisson's ratio. I can characterize whatever you want. I just need these two metal parameters. But when I am dealing with composites, it's not isotropic in nature normally. My dear friends, it's either transversely isotropic, sometimes orthotropic, and transversely isotropic, orthotropic, and yes, in very few cases, it is also isotropic as well. So characterization of these composites is still a very challenging task. That's why composites is still an area of focus researched. Weak in transverse direction. I am talking about fiber. Along the length of the fiber, if I'm talking about a long fiber having a diameter of 1 micron and a length of around 10 centimeters. If you have a thread at your home, surgical thread, just stretch it in tension. What is the strength? You will say, okay, some strength is there, but compress it, no strength. Against compression, there is no strength. But along the thickness, if I start applying the tensile loading, you will realize that along the thickness of the threads will start damaging, but it does not have much strength. Similar is the case in composites. Along the length, superior strength, but when I am talking about transverse, the strength got reduced. Other thing is difficulty in joining and repairing. I was working in NDPC. I still remember turbine blades. Regularly, annually, we check the turbine blades for wear, tear, any crack formation. We have magnetic material, magnetic powder. We have many techniques. Magnetic powder can be used for subsurface damage, defects, ultrasonic testing, and many other things that can be used with metals. What about composites? A polymer composite, it is not magnetic. It will not give you a response again magnetic. Many non-destructive testing will not work. So structural health monitoring of composite structure is still a challenging task, my dear friends. I cannot, still it's a field where research is still going on. Other thing is joining. Two metal pipes, how you will join? You just make a coupling. You can use the coupler. What about composites? Yes, we can use mechanical joining, but when I drill a hole in a composite plate which is having a fiber, the fibers will get damaged. I cannot really use the mechanical joining methods. So this area is still an area of research, and my PhD in Canada was based on adhesive joining of composite pipes. Despite having so much flow and everything, we are developing different types of adhesives that can be used for the joining of the pipes. It means we are, instead of joining mechanical means, we are looking at adhesives. Environment degradation, sometimes these polymers start absorbing moisture. This is another limitations that we have. Dreamliner, in India we are having Dreamliner, Airbus 380. Have you saw these big flying machines? What is the advantage that we have with these? The number of passengers that they can carry is really huge. Airbus 380, around 800 passengers can board and deboard. 800 passengers can go once in a time. Engines, same engines, slightly higher. But how this is possible that we are making these kind of huge planes without much changing in the engines? And the reason is 50% of the major structures are made by carbon fiber reinforced polymers. It means we are replacing the metals by these five composites. 50% is a big amount. We are replacing 50% of the metals by using 20% fuel saving. We are saving fuel, and then I will say one piece of fuselage. It means, you know, the fuselage, the big structure in which all passengers and everything is going from top and the bottom. If instead of making it from different components, metal components, if I make it by in a single shot, I do not need, my dear friends, bolts, fasteners. Otherwise, you need at least 50,000 bolts and fasteners. What is going to be the weight of 50,000 fasteners? It's huge. In terms of kg, it's really huge. But if I make it in a one shot without making any joint, it will save a lot of weight. Despite having a superior strength, it is very low in weight. These are some of the examples. These are some more examples that we have when we are talking about composites. Racket is one of the good examples. Now these days, these shafts, pipes, cycles, pressure vessels, we are using. Now comes to the mechanics. Terminology in composites, what exactly? On the left hand side, you can see the cylinders, a square, cube. I am considering this cube as a composite. The pipes that you see, the cylindrical pipes, it's a fiber. It's going from one face to the other face. So I can call it a unidirectional lamina because fibers are perfectly aligned along the length. I will say that this direction is represented by Z, my Z coordinate. As you see in below, XYZ is replaced by my Z coordinate. Then on the next figure is lamina. It means the thickness of this lamina is the thickness of slightly higher than the thickness of the fiber. You can clearly see single fiber along the unidirectional lamina, along the length of the fiber. It means I call this as the lamina. Now I have many laminas, one over the other on the right side, and I call it laminate. Stacking of many laminas one over the other. What is this plus minus theta s? Plus theta means now the fiber direction, the lines that you can see, the black solid lines, is the direction of the fiber. Now you can see it is not going from one face to the opposite face. It starts from one face and is going to the other face at an angle. And that the angle that it makes with the direction, x direction, I am referring this as plus theta. If the rotation change, orientation change, I call it minus theta. Why it is symmetrical? If you see plus theta, minus theta, they are same in number and they are making a symmetrical laminate. Now here in this figure, bottom figure, X, this is a composite plate. I am looking from the top. Composite plate is lying over its in a plane. I am looking from the top. I can clearly see X and Y are my global coordinates, whereas 1 and 2 is the direction of fiber. My axis 1 is aligned with the length of the fiber, whereas direction 2 is aligned with perpendicular to the fiber, or I can say transverse to the fiber. X and Y are global coordinates that is making an angle theta with the local coordinates. I hope that you understand these terms because when I am going to deal with the mechanics of composites, I hope you understand basics. Now, another terminologies that we are using: fiber. You can see on the top left, fiber plus matrix. When I mix these two, I will get a composite. When I got this composite. You can see over here composite. I want to apply macroscopic analysis. I want to perform a macroscopic analysis. In macroscopic analysis, I won't see fiber. I won't see matrix. I will see a plate, a rectangular plate. You can see over here, homogeneous orthotropic layer. In this case, this plate, you cannot see any fiber because I homogenized it. I have a single Young's modulus that represents the overall composite that includes my fiber as well as matrix. And this type of analysis is known as or referred as macro mechanics of a lamina. Macro. This is referred as macro analysis of a lamina. But if I still looks at separate fiber, separate matrix, I am analyzing it at a separate level. I call it micro mechanics of a lamina. It means I am dealing with separately with fiber and with matrix, a detailed analysis, and I call this as micromechanics of a lamina. Characterization techniques. These are some of the characterization techniques. I am just skipping this characterization techniques. Experimental ones, when we characterize by using experiments, manufacturing, computational ones. These are some of them, but I am skipping this. Modeling regimes. When I am modeling, what do we mean by modeling? Means if I am simulating this behavior, what scale I am looking at? Nanocomposites, I am looking somewhere at scale that I can see the atoms. I can call it, I can use structure of defects, DFT and MD. When I'm talking about composites, normally I will look at finite element based. It means I'm looking at some higher scales over here. So these are some of the scales I am talking about when we are dealing with modeling of these nanocomposites and composite. But I am skipping this slide, so don't worry, I will explain it once again when I deal other. Isotropic and orthotropic. Micromechanics of a composite lamina. Homogenization. What is homogenization? I talked about this term homogenization in my previous slide. Before I will go to the next slide. Professor Verma, are you listening me? Hello? Is there anyone who is listening me? Oh, so you are with me because I was speak. Okay, okay, okay. So okay, then fine. So there is a isotropic and orthotropic material. So I will start. What is homogenization? This term is commonly used. Many homogenization techniques are there, but I'm not going in detail. Homogenization, an equivalent homogeneous material sheet having the same global stress and strain relation as the heterogeneous lamina. What is meaning of heterogeneous? Heterogeneous means when I am talking about different. I have a different fiber. I have a matrix. It means I am looking at these two things separately. Fiber, matrix. I call it heterogeneous lamina. What is homogenized? Homogenized means I am not looking at fiber. I am not looking at a matrix. I use some mathematical means to get a single Young's modulus, single Poisson's ratio, single tensile strength as a composite plate. I call it homogenized, like steel. Can you, whenever we are talking about steel, I whether we are talking about iron, carbon, or this thing? No, I know what is the Young's modulus of steel. Homogenized properties. Same thing is over here. Homogenized properties. Now, extreme left, isotropic. You can see over here isotropic. Isotropic means you can see a white white rectangular plate having a width of W, length of W, undeformed. When I applied the load, it starts deforming, and the deformation is going to be have, how we can define deformation by using Young's modulus stress and strain relationship. Orthotropic. I understand. I hope that you understand what is orthotropic material properties. Normally in orthotropic material properties, the properties are different in three orthotropic region, X, Y, and Z. In X direction, properties are same. In Y direction, properties are same. In Z direction, properties are same. I need 9 independent parameters to define an orthotropic material properties. How many I need to define an isotropic material properties? Normally, I ask this question to the audience. 2, Young's modulus and Poisson's ratio. If we move from orthotropic, if you see over here, orthotropic, I will say that, okay, it's a fiber. Fibers are aligned in one direction, starting from one edge and ends at the other opposite end, this one. When I go to the lower side, I can clearly see when I deformed it in this direction, it is it is transverse to the fiber direction. This is representing transverse to the fiber direction. When I doing this along this direction, it is aligned with the fiber direction. So normally composites or laminas have higher strength when it is deformed along the direction of the fiber as compared to perpendicular to the direction of the fiber. What is this case? This is the case when fiber is oriented at an angle. So my dear friends, if we decide what is going to be this angle theta, I can easily tailor the properties of this composite. I can tailor the properties along the unidirectional as well as along the transverse direction. That's why I use that term tailored. Quickly, we all learn this thing from our BTech first year, stress strain relationship using Hooke's law. What exactly I did over here? If you see this matrix over here, strain and stress relationship, and what is this? It is representing my stress tensor with my strain tensor. And what is the C? Here C is representing my stiffness matrix. And what is S? S is representing my compliance matrix. And here you can see the properties. We all handle these properties. Epsilon X is the stress strain in X direction. Sigma X, stress in my X direction. 1 oblique E times this. You can easily solve this matrix. This multiplication matrix, tensors, multiplication of these. So I can easily calculate what is going to be strength in the direction of X. This is isotropic material behavior. And these are my stiffness matrix. Very commonly, you can see over here how many material parameters I am using over here in this matrix. Top right, E and mu, only two. This is isotropic. What about G? My G is dependent on E and mu. If I know E and mu, I can easily calculate G. G is equal to E divided by 2, 1 plus mu. We all remember, we all know that mathematical expression. I can easily calculate out. This is the expanded form. I just take the inverse of this matrix and I will get something like this. And I can calculate what are the stresses if the strains are known. In this case, I can calculate what are the strains if the stress values are known. Similarly, I have this is the stiffness matrix where I have all the 36 corners, C11 to C16 and C61 to C66. This is stress and strain relationship. I am not going in detail. I already explained you this matrix. This over here on the extreme right or on this side is just the short form of this. I just replace this C11, C12 and C13 with material constants. Again, classification when I am doing that extreme right one, top, isotropic material. I'm talking about an isotropic material. Red one at the bottom right. I am representing an orthotropic material. I need 9 material parameters. I am not giving the material parameters, but the material parameters are Young's modulus E in X direction, Poisson's ratio in X direction, and my G in X direction. Similarly, I have 3 for the Y and 3 for the Z. So I have 9 material parameters. What is this blue one? The left bottom. It is representing the material or the stiffness matrix of my transversely isotropic. What is transversely isotropic? What is transversely isotropic material? What I am again talking about. If you see this bottom one, a red color box, and if you see the small dots, white dots, perfectly aligned along one direction. On if I go back and I will see over here, in this case, over here, the second image, this image. What is transversely isotropic? If I apply the load, if you see this one, a small one single fiber surrounded by the matrix making a cuboid. If I apply the load in the transverse along the direction of the fiber, I can clearly say that it's having a single properties. It's having a E, it's having a mu, it's having a G. Okay. What about when I start applying the load in the direction that is perpendicular to the fiber direction? If I take the fiber direction as X, if my fiber length is aligned with the X direction, what will happen if I apply a load in Y direction? It will happen having a properties in Y. What will happen if I apply a load in Z direction? The Y and Z directions will have the same properties because this fiber, if you see, is perfectly circular. It is aligned along the length. So perpendicular to this, in this directions and in this directions, the properties will remain isotropic same, and we call it transversely isotropic. Where is this transversely? If my fiber is aligned with the x direction, then in y and z direction, my material properties will remain same. That is a direction that is perpendicular to the orientation of the fiber, and I call it transverse to the fiber. That's why we have this transversely matrix. Just give me 1 minute. I will just have a sip of water. Now, what about designing a lamina? When I'm talking about designing a lamina, you see in my previous slide, in this, the width of the fiber is very low. I'm talking in microns. Over here, in previous slide, if you see a lamina, what is the thickness as compared to length and the width? I will say the thickness is negligible. It's very low. I cannot compare it. So straight away, when I am applying stress, when I want to calculate stress and strain, the first thing I do, I will assume plane stress assumptions. I will assume plane stress assumptions that will help and simplify my case. So now the stress and strain relationship is reduced. Earlier, I was dealing with 6x6 matrix. Now, what exactly I have in the red boxes? You can clearly see. Instead of 6x6 matrix, now I am dealing with a 3x3 matrix. My life is more simplified, much comfortable. So here you see the compliance matrix reduced to S11, S12, S12, S22, S66. Here I have strain, here I have stresses. In terms of Young's modulus and all these things, I can mention it over here, E1, E2, because I'm considering it orthotropic in nature. So my E1 and E2, I mentioned these two different properties, sigma. When I'm talking about sigma 1, sigma 2, stress and strain relationship, I'm using this Q. Perfectly fine. Now, macro mechanical analysis. If you see over here, when I want to calculate stress, I want to calculate strain, I just need S11. If I want to calculate shear component, I need S12. Perfectly fine. This makes my life much more simple. What about when the fiber is at an orientation? What happens with the stress and strain relationship? Because whatever I am talking over here, it is in the case when the fiber is in one direction. X direction. But when my fiber orientation is in between X and Y direction, what will happen to this S matrix and Q matrix? So my dear friends, when you are macro mechanically analyzing a laminate, the only thing that you need to do, you want to find stress and strain relationship, material properties, everything. What do you have to do? You have to calculate S bar, Q bar. What are these S bar and Q bar? S bar and Q bar are reduced stiffness and reduced compliance matrix. What exactly? It depends on rotation matrix. Can you see on the top one? What is sigma xx, sigma yy, tau xy? What is sigma 1, sigma 2, tau 1, 2? Sigma 1 is the stress in direction 1 that is aligned with the direction or the orientation of my fiber. What is sigma x? Sigma x is the x direction of my plate, my global coordinates. I am talking in terms of plate because I know, okay, my dear friend, I want to calculate stresses of this plate in this direction. I am not talking about fiber. I don't worry about fiber. I want to calculate in this thing. But at the bottom, that orientation of the fiber is playing a crucial role. You can see over here. I can transform the stresses in this. What is T inverse? T inverse is represented by this, where C is cos theta and S is sin theta. And we call this whole matrix as transformation or the rotational matrix, which is represented by T. What is this S bar, Q bar? What is S11? I know what is my S11. What is my S11? S11 is 1 oblique E1. This is the case when my fiber is perfectly oriented with X direction. I get these properties from experiment. I have these properties in books. Unidirectional properties are in books because we already calculated it by using experimental means. I have 1 oblique E1. I have properties in unidirectional cases. But as I start rotating and I start manufacturing composites with different orientation of the fibers, my dear friends, I need to calculate what is going to be the reduced stiffness and reduced compliance matrix. These are the equations that can be used for calculating those S bar and Q bar. S bar is written over here. You can see over here. and Q bar is here. S bar and Q bar are functions of angle theta. S11, I know what is my S11. What is S11? S11 is 1 oblique E1. What is my S12? I know what is my S12. S12 is minus mu12 by E1. So in this manner, I can calculate it for angled lamina. I can calculate it angled lamina. So this is basically macro mechanics. Macro. Macro means when I am calculating this in this, I can straight away go and calculate what is going to be the stress of the composite, stress of the lamina. Here I am not talking any term, stress in fiber, stress in matrix. Have I discussed anything about stress in fiber? I am talking about global stresses, local stresses. Only coordinates are changing, but I am not talking about, I'm only talking about direction. I am only talking about direction, but I am not talking about fiber and matrix separately. I am talking about lamina. I am not looking at fiber and it is just like moon. I am looking from moon from here. It looks like a perfect sphere. But if I go closer and closer, it's not a sphere. I will start seeing there are hills, there are craters, and these things. When I start analyzing this, oh, you are doing a micro analysis of moon surface. Micro. I am going in more detail. I am going in more detail. So now I am switching to micro. Micrometers. I am from meters, I am moving to micrometers. Smaller level. Next, left side, non-homogeneous lamina, micromechanical analysis. You can clearly see the fibers. Right side, homogeneous lamina, macro analysis. I am not talking about fiber. I am talking about overall properties, average properties. One most direct way to determine the material parameters is through experiments. However, experimental evaluations are usually quite expensive and time consuming, especially when I am dealing with nano composites. It's really difficult to experimentally characterize nano composites. So still we are making different models that can give us an idea whether this composite will work or not, nano composite will work or not. Objective of the micromechanics of a lamina is to protect these mechanical properties based on the properties of its continuous fiber matrix and volume fraction. Now, here comes assumptions. As we are going in detail, more finer details, and we are trying to make models. Why we are looking at micromechanical analysis? Because experiments sometimes will not give us the exact physics. So we are developing analytical models, numerical models, atomistic models, quantum mechanics based models to get more detailed analysis, and we call it micromechanical analysis. When we start doing this, we are making models, mathematical models. Mathematical models are complex in nature. In order to make it more simplified, we come up with assumptions. What is the first assumption that we have? The fibers are uniformly distributed in the matrix according to certain pattern, and all fibers have same radius. It means I am going to do micromechanical analysis, but I am assuming something before starting my analysis. I am assuming that all my fibers are of same length, same diameter. They are arranged in a perfect manner, as you can see, in a hexagonal manner, in a square manner. This is the way how I can study these, because I cannot go and study each and every fiber. I am assuming this thing. This is the first assumption that I have when I am dealing with micro. So when I am talking about composites, I start with macro analysis. First, I look at a broader spectrum. Okay, I have a lamina. The Young's modulus is this much. Poisson's ratio is this much. I don't care. That's the thing that is helpful. Now I'm going